Alright, so getting started, graphing linear relations. Data and relationships, we can represent them using both graphs and equations. This shouldn't make too much of a surprise for you. Obviously, we've graphed data before. And the question that we would want to ask ourselves eventually is it possible to have a graph and an equation representing the same information and relationship? And then furthermore, how would you determine whether that graph and the equation are the same, whether they're showing the same thing? So a linear equation, if we're going to define that, is going to be an equation. This is going to be super neat writing. An equation where the variables are not to any exponent. Okay, so if you have an x, it's just an x. It's not x squared or x cubed or anything like that. Also, so an equation where variables, there's more to it than that, but we'll start with that. This is some of the neatest writing you're ever going to see. Variables are 2 to the power of 1 and it makes a straight line. You can add that part. It makes a straight line on a graph. Alright, so let's take a look here. World's largest cruise ship, at least when your textbook was written, called Freedom of the Seas, uses fuel at a rate of 12,800 kilograms per hour. So the fuel consumption in kilograms can be modeled using this equation. F is equal to 12,800 T, where T is the number of hours traveled. So our first step, what we can do with this is let's build a graph. If we're going to make a graph from a linear equation, I look at that initially and I'm like, well, how do I do that? But the thing is, make a table of values. Okay? When you make your table of values, take a look at your equation. Usually you're going to have one variable on one side and the other variable with the numbers and coefficients and variables, and sorry, the other variable with the coefficients and any other free numbers on the other side. So what we're going to do is we're going to put the t, the one that has all of the stuff with it, on the left side, and we're going to put the f on this side here. If we're talking science, this t is going to be the manipulated variable, the f is the responded variable. So it doesn't make sense with our cruise ship, or anything else for that matter that's consuming fuel, to talk about negative numbers, but we could start with a negative time. We could start with 0 hours. Okay, so time is 0. That's easy multiplication. I can do that in my head. Fuel consumption is 0. Yay, look at us go. Time is 1 hour. Fuel consumption, well, 1 times 12,800 is, you got it. I can do this in my head. It's gonna stop soon, but 2, okay, multiply 12,800 by 2, because we put in t here. F is equal to 12,800 times t, and this is going to be 25,600, and so on. Now, in order to make a graph, you need at least 3 points. I always recommend don't have them all right next to each other. Let's do one. We want the first 7 hours. Let's do, okay, we've got 0. Let's go up to 7. Okay, so figure that number out. 12,800 times 7. Then we're going to set this graph up. Okay. is some of the prettiest axes you'll ever see. You should use a ruler to make yours. Okay, I'm going to start down here. We've got 0 and 1, 2, 3, 4, 5, 6. Oh, I did not put that in the right place. Let's move it over just a smidgen. Ooh. 0, 1, 2, 3, 4, 5, 6, and 7 hours. On this side here, now we could go up by, I guess, 6,400 for every one of these things. That would probably be easier. And then this 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, 7 hours. Okay, I'm going to let you make the graph here. You're going to discover that yes, it is a straight line. Okay. To make a straight line, you need at least 3 points. Always a good idea. Do at least 3. 4 is not a bad idea, but don't go for overkill. Alright, you'll have a nice straight line. Now we can figure out approximately how much fuel is used in 11 hours. Now we could extrapolate. We can make our graph longer with the scale that I gave you here. That's going to be challenging. How else could you do that? We take this 11 hours, that's a time value, plug it into the equation, and we can get F is equal to 12,800 times 11. That'll give us our answer here. How long can the trip travel if it has approximately 122,000 kilograms of fuel? Again, we could extrapolate or interpolate, depending on where the number is. Okay, I'm not trying to give anything away to you here. I'm going to make you figure it out. Or do a little bit of algebra. This is an fuel number, so this could get plugged back into our equation here as 122,000 is equal to 12,800 T. Now we've just got algebra. Okay, so we can either do equation and algebra stuff, or we can look on the graph and either interpolate or extrapolate. Alright, so what is the first step in graphing a linear relation? I want you to say it out loud to your neighbor. Your neighbor needs to be a grade 9 student, not just some random grade 7 or grade 8 student and you're being a distraction. First step in graphing a linear relation is make a what? Yes, a table of values. Okay. What goes where? Well, we've got the y is all by itself. It's going to go on the right hand side. The x has got other stuff with it. It's got constants, -5. It's got a coefficient, 2. So it's going to go over here. Now, is there anything to stop x or y, for that matter, from being negative here? Definitely not. So let's start with, I don't know, -5. So we plug in -5 for x in there. 2 times -5 is -10. Minus 5 is -15. Okay. I'm going to let you do the rest here. Pause it. I'll kind of show you what you're going to have, but pause it. Please go ahead and pause it. Alright, so I've done a little bit of work for you here. I graphed 3 points here. You could definitely connect these with a straight line. Use a ruler, please. Okay, and away you go. So then we look down here just a bit. So use the graph to estimate the value of y if x is equal to 8. So I've got 5 plotted here. 6, 7, 8. You're going to have to extrapolate. Alright, so you're going to take a look at your line. It's going up in here somewhere, and you're going to have to do your own. I'm making it sloppy on purpose. So we look and say, okay, if x is equal to 8, so we find x is 8. We go up to find the line. There, we found the line. And now we're going to go over to find where we are on the y-axis. Okay, your scale may be different than mine, but the numbers should be the same. Given that my scale here is that each value on the y-axis goes up by like 2.5, it's going to be hard for me to be super accurate, and then there's the other problem that, you know, drawing straight lines is challenging also. So, do the figuring there. Use the graph to estimate the value of x as if y is equal to negative 4. So here we go, okay, y is negative 4. Now it's going to be somewhere here. We're going to go this way just a smidgen. And then we go up to find out what the x value would be. Okay, so we're doing some interpolating, some extrapolating here. We can use the graph to figure out those answers. Then you can verify your answer using the equation. So with this one here, we plug in, okay, what's y if x is 8? Well, x is equal to 8. So we plug that into here. Y is equal to 2 times x minus 5. 2 times 8 is 16 minus 5 is 11. And that's what we should get. Down here, y is equal to negative 4. So, okay, negative 4 is equal to 2x minus 5. Let's add 5 to both sides. And at this point, we're going to have 1 is equal to 2x. Divide both sides by 2x is equal to 0.5. Example 2, we're going to graph some horizontal and vertical lines. These are the easiest graphs you're ever going to do, okay? Now, when you're doing these graphs, and this follows you into high school science, high school math, whatever you have a table of values. This first number always, always, always goes on the x-axis. Sometimes it's going to be labeled x, sometimes it won't, but that's going on the horizontal or the x-axis. Okay, so if we do this first one here, what you should notice here is no matter what the time is, the distance is always 6 meters. So 1, 0 seconds, so we've got 0, 30, 60, 90, 120, yep. This is 6. You can label these 0, 30, 60, 90, 30, 60, 90, 120, 150, so on. Okay, so dot there, a dot there, another dot there, another dot there, another dot there. I think I've got enough. Lovely. You can see this is going to make a horizontal line. Okay, take a look over here. So we've got a x versus y graph. Okay. Build our axes again. Everything's positive, so I don't need to make a whole quadrant. So in this case, oh well, let's go 0, 0.5, 1, 1.5. And then we've got the height is going to go 1, 2, 3, 4, 5. Right? So, like 2 over here. So now the thing is though, no matter what our x value, no matter what our y value is, x is always 1.5. So we're gonna have here's okay. Y is 2.5, 2.5, and 1.3. There it is. 3.5, yep, there it is. 4, yep, there it is, 4.5. I hope you can see this is a nice vertical line, even on my terribly drawn graph. Okay, so describe a situation this graph might represent. So here we've got time and distance. So perhaps in this case we've got a car that moved 6 meters from someplace, and then, well, it started out 6 meters from someplace. Maybe it's out of gas, and it just sits there. It doesn't move. Just sitting there, not moving. That's possible. Alright, something that's moved X meters along the ground and is moving upwards. Well, this sort of looks like maybe we threw a ball up in the air. Right, the ball started at 2.5 meters, so it was already 8 feet up. It's apparently currently, and then we're just throwing it straight up in the air. And eventually it'll come back down, but for now it's just going straight up. Okay, that would work. Write the equation. Now, horizontal and vertical equations are really easy, but you got to look at your variables here. So for the very first graph, this axis here is the time, and this axis here is the distance. So for the first one, does the time matter? No, it doesn't. Right? No matter what the time is, it's always at 6 meters. So for the first one, the distance equals 6. Very easy table of values also. Because it doesn't matter what you put in for time, distance is 6. Second one here, we've got x and y. Well, here, doesn't matter what y is, x is always the same. So, second one, x equals 1.5. No matter what y is, x is 1.5. Alright? So, your turn. Write a linear equation that represents this. Explain how you know the graph matches the equation. So pause it, do the work. Come on, pause it. Good job, pause it. Yeah, good. Okay, pause it. Hopefully you paused it. Distance is 4. It stays the same. How do I know the graph matches the equation? It's no matter what I have for time, it doesn't matter because the distance is always 4 meters. Alright, this takes us to the toughest part of this section. Alright, so we've got determining a linear equation from a graph. Now in this case, we have a nice table of values. If they don't give us a table of values, make a table of values. Okay, read your graph, make a table of values. Okay, now there's a lovely graph. Great Slave Lake, Northwest Territories, you can find it on the map if you want. It is the deepest lake in North America. Maximum depth is 614 meters deep. Sam decided to check the depth using his fish finder. He collected the following data up to a depth of 180 meters, which was the maximum depth that his fish finder could read. So there it is. There's the data. He made a graph, or got lazy and made it on a spreadsheet, I should say. What linear equation, does this graph represent? How do you know the equation matches? This is the tough part. We are going to have to figure out patterns here. This is something you would have done already back in like grade 6, but it's been a while. So let's take a look here. What do you see? Well, this goes down by 35, and it does the same thing every time. Well, that's going down by 35. This is going up by 10. Right? And that continues all the way down. And boom, 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 boom. Okay, great. Now, the question you got to ask yourself, and this is what's really going to make your life easy, is to say, okay, if the distance increased just by 1, how much would this change by? Well, if it's going up by 10, this goes down by 35. So we could take 35, divide by 10 to figure out how much it goes down each time. This is nice math, at least. So for every 1 distance, the depth drops by 3.5 meters. Right? So we could kind of make a new little 0, 1, 2, 3, 4, and so on. We could just make a new version of this. So at distance from shore, obviously the depth is 0 meters. 1 meter from shore, it's negative 3.5 meters. 2 meters from shore, negative 7. 3 is negative 10.5. 4 is negative 14. Oops, and so on. Now the question we got to ask ourselves, what do we have to do to get from here to here? Now, every time we go, this is the important part. Every time this side goes up by 1, this side goes down by negative 3.5. How do we know that? Once again, this goes down by 35 when this goes up by 10. If it's a linear equation, which we're being told we have to assume it is, then that's going to be true even if we divide this by 10 to figure out what it is if it goes, distance goes up by 1, and we divide this by 10. Okay, it's got to be the same. Now, it's going up by 3.5 every time. There's going to be multiplying by 3.5. And so the question we got to ask ourselves is, okay, so it seems like the water depth is equal to the distance from shore multiplied by negative 3.5. Negative 3.5 times the distance. Now, there sometimes is going to be like a plus or minus, some kind of a constant in there. But the thing to always do is to check this with the first couple to see. So, W equals negative 3.5 D. So if D is 0, negative 3.5 times 0, hey, that's 0. Okay, so it works for the first one. What about the second one? W equals negative 3.5 D. So, negative 3.5 times if D is 1, is equal to negative 3.5. Okay, think back to, like, I don't know, this is grade 6 math. And input-output machines, I think they called them often. Okay, let's try it for 2 just to make sure. Okay, depth is 2, so negative 3.5 times 2 is, distance from shore, negative 3.5 times 2 is negative 7. Hey, it works. So our equation is W equals negative 3.5 D. Now we've checked it for a few little values. We can also check it for one of the bigger values. So we can look and say, okay, well, 30 and negative 105. So what is negative 3.5 times 30? And what we're going to find is that that is going to be negative 105. It works. Lovely. If the pattern continues, how far from shore would Sam be when the water was 614 meters deep? Well, in this case, W, our water depth, is going to be, so we've got our equation. Let's write it down. W equals negative 3.5 D. And W then is 614. 614 is equal to negative 3.5 D. Solve. Sorry, 614 meters deep means it's negative 614 meters. And we're going to solve for D. So I'm going to divide both sides by negative 3.5, which I can't do in my head. Perhaps you can today, and you're just amazing, but I'm not that amazing. D is equal to, I'll take our calculator, 614 negative divided by 3.5, also negative. Distance is about 175 meters from shore. Now, my own personal question is it an actual, like a straight line drop off like this? Or is there something else going on? And probably it's actually something else going on. That it probably doesn't go straight down like this and then just flat 614 meters deep. However, that's neither here nor there. At what rate is the depth of water decreasing? So here we're looking at something per meter. Well, how much does it change per meter? Well, it goes down by negative 3.5 meters per meter away from the shore. This comes back to my little point. Is it appropriate to interpolate or extrapolate values on this graph? Well, interpolation, probably. Extrapolation, obviously the maximum depth is 614 meters. So we couldn't plug in distance from shore of, I don't know, like 3,000 billion or something like that. That's not even a number. 3 trillion. Because it's going to get to be too deep. Okay? So extrapolation in this case will run into problems. Interpolation, probably not too bad. Although we don't know, with his fish finder, does the bottom of the lake do like this? Right? Catching all those points, but like being very undulating other than that. We don't know. So interpolation, use it cautiously. In this case, extrapolation, probably hard to use that one. Okay. Identify the linear relationship that represents the graph. Same thing here. First thing, build a table of values. We used the table of values they gave us last time. This time we got to do it ourselves. So when we have ordered pairs, they are always in the form of x, y. It's a good thing I said that because that looks like garbage, but that's all right. On this side's always going to be our x, and this side's always going to be our y. Okay, so x, y, 2, 3, 4, 4, 6, 5, 8, 6, 10, 7. What do we notice? Well, this goes up by 1, and this goes up by 2. So the question I'd have for you is, what is y going to look like, for example, at 3? Well, 3 to 4. This is 2 to 4. 3 is halfway between 2 and 4. Go up by probably 0.5. It's going to be 3.5 there. The other way we can look is, okay, this goes up by 1. The y value goes up by 1. The x value goes up by 2. If we want to find out how much y goes up if x goes up by only 1, let's divide both sides by 2. And what we're going to see is, of course, that this goes up by 0.5, right? 1 divided by 2 is 0.5. So if we want to kind of rehash out our table of values, x's and y's, and this is going to be, let's say here, 2, this is going to be 3. At 3, y has gone up by 0.5, so we've got 3.5, 4, 4, and so on. Now this is a little bit trickier, because this is going up by 0.5, which means we're going to be multiplying by a 0.5. Okay? Whatever this goes up or down by, once we figured out what if x is going up by 1, whatever this goes up or down by is going to be important. This is going to be what we multiply that by. So when we write out our equation, the first part of it's going to be y is equal to 0.5x. And it's going to be plus or minus something. Because we got to go multiply 2 by 0.5 and then add something to it to get to 3. So one of the ways we can do this is, I'm going to rewrite this little table of values again with 3 columns. So we're going to have x and y. And this is basically, the middle column is going to be, what do we do with x to get to y? So if we've got 2, and over here is 3, well, the first thing we're going to do is going to do 0.5x. So 0.5 times 2, what is that? That's going to be 1. 1 plus what gives us 3? Oh, it's going to be plus 2. Is equal to 3. Lovely, okay. That works for that one. Does it work for 3? Okay, well, 0.5 multiplied by 3 is 1.5 plus 2. 1.5 plus 2 is, hey, it's 3.5. This seems to be working. Let's try it just for one more, just for fun. Let's go for 10. We've got that one there. 10, so we've got 0.5 times 10. Plus 2. 0.5 times 10 is going to be 5 plus 2 is, hey, it's 7. Does that work? That's the right number. Okay, we've done it. So your job here is to just work through this. If you need to listen to this last section again, do that. Key ideas. You can graph a linear relation represented by an equation. Use the equation to make a table of values. Write it out neatly. I can't, but you can. Graph using the data from the table. The graph of a linear relation forms a straight line. Graph of a linear relation can form a horizontal or a vertical line. You can use, this is good, you can use good grammar as well. You can use the graph to solve problems by interpolation or extrapolation. Sorry, this should be interpolating or extrapolating values. We're making it into verbs. We're verbing it. Which you can check with your language arts teacher if that's good grammar. You can use equations to solve problems by substituting values into the equation. That's the really powerful part of this tool. Is sometimes, like, let's go back to this graph here that I skipped. Oh, no, this one up here. Really hard to tell what the numbers are from the graph. But if you've got the equation, w equals negative 3.5d that we built, we're good. We can do whatever we want and get accurate data. So to determine the linear equation from a graph, make a table of values. That seems really important. Yes, you got to do it. And determine the pattern or relationship between the two variables on the table. We're always going to be looking at how do I get from the first variable I've got written to the second. What do I do mathematically? Multiply, divide, add, subtract to the x to get to the y. Okay, this is my input. This is my output. How do I find a rule that gets me there? And that's really what we're doing. Good luck, have fun, do as much as you can. If you have trouble with part of it, do as best you can. If you're really struggling and this stuff is all hard, talk to the rest of your classmates. Okay, don't try to go at it on your own. That's the first thing. Secondly, if you're really struggling, move on to after 6.3. The next section after page 243 is going to be some review stuff. Start on that. The first two parts of the review you can easily do. Thanks and good luck.